Hey everybody, I hope you're doing well. In this video, I want to talk about why this subset actually forms a subspace inside of Pn. Well, to show us something is a subspace, I got to show two things. One, it's not empty, and two, that linear combinations are also an element of W. So let's start off with non-empty here. All right, so I claim that 0 is an element of W here. Okay, why is that? So if I take a polynomial and I set it equal to, not set it equal to 0, I'm defining the polynomial to be 0, then I know that r double prime of 3 minus 4 times r double r single prime of 4, well, that's equal to 0 minus 4 times 0, which is just 0. Because if r is 0 to begin with, we wind up getting the derivatives, and the second derivative is equal to 0. So I already know that the 0 vector is an element of W, so this is not empty. So what about the idea of linear combinations? All right, so let's start off by picking two arbitrary polynomials. I'm going to call them P of X and Q of X. And I'm not saying this P up on the top here. I'm just saying I have two polynomials that happen to satisfy this idea up here. So with that said, I'm going to construct a new polynomial here. I'm going to construct r of x. That's going to be some multiple of p of x plus another multiple of q of x. Now I want to show that r satisfies that condition on top with a first and second derivatives. So in order to do that, let me take a derivative. Now, alpha is a constant, so it's going to come along for the ride. Beta is a constant, so that's going to come right. And if I take a second derivative, well, it's going to be the same process here. Now, what do I need to do? I need to look at r double prime of 3, and then r prime of 4. Well, specifically, I need to multiply this by negative 4. Now, if I do that, I get alpha p prime of 3, double prime of 3, plus beta q prime of 3. I mean, double prime, I keep doing that wrong. So that's what r double prime of 3 is. Now, my other one, I'm going to have negative 4 alpha p prime of 3 minus 4 beta q prime of 3. Now, what I notice here is that I set this up in columns. So if I look at this first column right here, I'm just not talking about a matrix, I'm just talking about a column. What do I wind up getting? Well, I see an alpha in each one of these. So I'm going to factor that out, and I wind up getting this. Now, what do we know about the vector p? Well, the vector p satisfies where this is equal to 0. So I know that this part here is equal to 0. Now, what I can also do is say, well, let's take a look at this piece right here. Well, q is also in w, so I also wind up getting 0. All said and done, I know that this new vector happens to be in w because it satisfies the condition that I need. So in a nutshell, what have we done here? One, I showed that something is not empty. Something of this W right here. Now, how did I do that? Well, I'm allowed to pick anything I feel like it as long as I can demonstrate that it satisfies the property that I want. So I show that W is not empty. Now, the second thing is I pick two vectors that are in W, and then I look at their linear combination. I want to show that their linear combination satisfies a condition like this up here. So I take the derivatives, and then I look at this condition here. I'm going to plug in 3 into the second derivative, plug in 4 into the first derivative, but I also need to multiply it by -4. And I do that down here. Now I lined it up so that these things sit on top of each other here. And this first column, I wind up getting this idea right here, where I can factor out this alpha out of both terms. I know that P happens to be in Q, so this particular expression becomes 0. Well, alpha times 0, but 0 is the additive inverse. Additive identity, my bad, and I know that multiplies 0. I get a similar thing for Q. Well, what does that mean? It says that R of X satisfies this condition, so it's an element of W. And that's about it. I hope you found this video helpful. If you have any questions, let me know. Bye.